Alrighty, non-homogeneous linear equations, okay? Last time it was homogeneous, meaning this side was 0, right? So if you take this as an example, there was no x squared here, it was 0, right? Now we have some function of x. So differential equation, second order, typically we will have y, second derivative of y, first derivative of y, the y itself, y being the function of x, and on the other side, some kind of function of x. So this is what this language means, right? Y double prime, y, and some kind of function of x. And that function of x, in this case, happens to be this. Okay? And there's a little technique, and there's a proof that this is a combination of the two, but I would rather want to take this example and then use that example to explain what this means. And then we'll go through this proof. Okay? So first, let's say we have this systems of equation, or system, ordinary differential equation of second order. Okay? First thing we're going to solve is homogeneous equation, which is y double prime plus y plus, let's zoom in a little bit, y prime minus 2y is equal to 0. Okay, we have to get a solution for this first. And we have done this before, but for the sake of review, I will redo this. So we try y is equal to e to the rx. That means y prime is equal to r times e to the rx, and y double prime is equal to r squared e to the rx. Right? This much we have seen before. And once we plug these three into this differential homogeneous without x squared here, then what we have is r squared e to the rx plus r e to the rx minus 2 e to the rx will be 0. Good so far? Now we factor, so e to the rx is a common factor, and then the rest of them is r minus 1, this is r, and then r plus 1 plus 2 will be equal to 0. Good? Since e to the rx cannot be 0, it means r is equal to 1 or r is equal to negative 2. Okay, so what we have is what we call the general solution. Okay, and for some reason they use subscript c, so I'll just go with c. Common solution, whatever. It was c1 and e to the rb1 x plus c2 e to the negative 2x. It was the combination of the two, now wasn't it? And we have done a little bit of proof by example on why both of them, but this linear combination works in here once you substitute. So far so good. Now, then I'm going to solve whatever is given to us, y double prime plus, what was it, minus, I wish I can remember, plus y prime minus 2y now is equal to x squared. Okay, whatever we get out of this is called the particular solution. Okay, and then now what should we try to get this is a question. Okay, of course, e to the thingy is a pretty good candidate, this thingy, but we did that already. So anything other than this. Now we look at this other side. Equations, right? Functions that if you take a derivative, then you have to get x squared. So you think second order polynomial would be a nice candidate to try? Because if you take derivative of polynomial, you still get polynomial. You know what I'm saying? So we'll try this. For this, we try y, particular solution, is equal to a x squared plus bx plus c. How's that? I mean, we can go higher order. We can have x cubed and x to the fourth power. But looking at this, those will turn out to be 0. You know what I'm saying? Because if you take any combination of first derivative, second derivative, and this function itself, and then yeah, it's plausible that you will get x squared. Let's see if that really works. This will give us systems of equation again. So y prime will be 2a x plus b, and y double prime of sub p will be 2a. Now we have to plug all of that in. Okay, so let's suck it up and do it. So y double prime is 2a, good, plus this one, 2a plus b, 2ax plus b, and then negative 2 of this thingy, ax squared plus bx plus c. Now that must be x squared on the other side. So far, so good. Like terms. So what we have is negative 2a. So we have negative 2a x squared is that x squared term. And x term we will have here 2a minus 2bx. Good. So we'll have 2a minus 2bx. Stay with me? And the constant will be 2a minus 2c, or b plus b minus 2c. So for circuit, and the other side is x squared. Does this remind you of partial fraction? Yeah, it's that kind of thing. So now comparing both sides, in order for the polynomial to be equal, all of the coefficients must be equal, right? So negative 2a must be 1. So that tells you a is equal to negative 1/2, right? So first of it. And then once you plug it in here, this whole thing, 2a minus 2b must be 0. There's no x on the other side. That means b value has to be exactly the same as a value. Too much algebra? Okay, now plug in negative 1/2 here, and then this whole thing, b minus 2c, needs to be 0. Good? So that should tell you c is equal to negative 3/4. So first circuit? Any confusion? Tell me if this is too much algebra, I can really show you. I do teach algebra too. Yes?
Is there ever a situation where you're not able to solve for A, B, and C?
If it's a simple one like this, then it always works. Now, if you have some complicated, that's a very excellent question. Instead of having x squared, actually, I have other examples coming up, but let's just talk about it. Instead of having x squared, if you have a sine and cosine here, or sine or cosine here, guess what this trie would be? Combination of sine and cosine. One would think, right? Because if you differentiate sine and cosine, you get sine and cosine. If you have exponential function here, then you try exponential function here. What happens if you have something like ln tangent? Then we get into trouble because there are no, you know what I'm saying? Then there's when we have a complicated function, then we have new technique, which is next section, right? So we'll fry that fish some other day, but so far, this method of undetermined coefficient, meaning undetermined coefficient A, B, C. You know what I'm saying? Because the function itself is pretty easy to take a guess. How about that? Okay, so now so what we have is y particular solution is a negative 1/2 x squared minus 1/2 x minus 3/4. Okay, now your entire solution, y, has to be your y of the common solution, general solution, plus your particular solution. Both of them. Really? Okay. So what is your y then? Your y should be this thingy here. Oh, this is a computer. I can do copy and paste. Copying and pasting should be easier than this way. One would think. This, and now I copy this thing. Whoa, why? Seriously, copying and pasting should be easier on a computer than this. Paste, combination of these two. Okay. Now, let's think about it. Why would it work? I mean, some of you can kind of see it. That's what this theorem is about, right? I think we can talk about a little more theoretically instead of doing this. Say, if you have a combination of the two, this particular solution here first, but if you take a derivative, you get these two, and if you take second derivative, you get these two, right? We plug it into the differential equation, right? The way the differential equation is designed is so it's like second derivative, first derivative, and just the function, right? Now you collect these things, like terms, if you will, particular solutions and general solution ones, okay? Now this thingy is designed to give you 0, because that's how we solved it here, right? With a 0. So if you plug it in, this will give you 0. Now this thingy, which is this side, this thingy, is supposed to work for this. So this thingy right here will give us that function, which was our x squared. That's all that means. So of course the combination, purely because one of them, this thingy, is supposed to be 0 once you plug it into the differential equation. You get it? So you get this. Now, if you don't believe me, you can actually take derivative and second derivative of this, and then plug it in, and you will get exactly x squared.
So essentially, you're saying that when you make the right-hand side of the differential equation x squared, it's x squared plus 0.
Yeah. X squared plus 0 is what you get. This will give you 0, and this will give you x squared. And that makes sense, right? The only reason this works is this differential equation thingy, this is linear. Linear meaning there's no see, this is what example of non-linear. If you had something like this times y, this is not linear. You know what I'm saying? But these are just additions with some coefficients. So for that reason, this works. If you have this going on, then it's not going to work anymore. And that's a more complicated college level differential equation. But so far, we're just doing easy ones. Good? All believable now? Okay, then we'll take another example. Now we have exponential. Okay? So let's see how this one works out. So first thing we do, of course, is this thing, y double prime plus 4y is equal to 0, right? Could we just skip writing, try this e to the rx, and if you plug it in, this one will give you r squared e to the rx now. And then this one is 4 e to the rx is equal to 0. Factor, so e to the rx, and then r squared plus 4 is equal to 0, right? So our r is equal to plus or minus 2i. Good? So our common solution will be c1 e to the 2ix plus c2 e to the negative 2ix. But the other day, instead of doing that, I told you it's so much better if you convert it into cosine and sine, right? Euler's formula. So we convert it into this. So first of it. Now, the other one we have to do is particular solution 1, which is y double prime plus 4y no prime is equal to now e to the x. Good? Now, guess what I'm going to try? That's my guess. To get that. Of course, some constant, right? C. and times e to the 3x as that. Now that's believable because if I differentiate e to the 3x, I will still get e to the 3x, 3 times e to the 3x, therefore some constant. You know what I'm saying? Okay, then I will say y double prime will be 9 times c e to the 3x. Good. Now I will plug these two into my differential equation. And let's see what that gives us. So y double prime is 9c e to the 3x plus 4y, y is c times e to the 3x. And that needs to be e to the 3x. You with me? So that tells you, combine it like terms, 13c e to the 3x is equal to e to the 3x. So that tells you c is equal to 1/13. Good. So our particular solution is 1/13 e to the 3x. And then our entire solution, of course, is combination of these two. Which I will also try to do copy and paste. This one here, and this one. That wasn't great, but I can, you know, copying and pasting should be easier than this. Like that. You get it? Now, you might wonder, what about a and b? This is constant, because we figured out the constant for the particular solution. How come we still have the constants of the common solution not figured out? That requires initial values, okay? Yeah, we don't have initial values yet, so those, this is a family cell. But this one is particular. It's called particular because we know what this is, because it all depends on this thing. It has to give you that particular function. The other two, you still need the initial value. So we did initial value problem before. Eventually, it will be combination of the two. So far, so good. Okay, we'll take one last example, which is this, sine and cosine. Move it up. Okay, let's do this. Okay, so this one, see, does this look familiar? Yeah, it's a recycle of this thing, isn't it? The left-hand side, homogeneous equation is exactly the same. So why don't I just recycle this? Okay. One second, copy and paste. Let's see. So we'll recycle this from example 1. Now, all we have to do is solve particular solution, this whole thing, okay? Now I have a sine. Take a derivative of sine, it will be cosine. Take a derivative of cosine, it will be sine again, right? So I'm gonna try this. This is my try. Try y particular is equal to a cosine, and then x, because I have x. Had I had 2x here, then I'm gonna put 2x here. If I had omega x, then I'll put omega x. You know what I'm saying? Whatever that will give, if I take two derivatives, it should still give me this. So I have to pick the one that will have a chance, okay? Not just any sine and cosine. Plus the sine of x, okay? Then y prime will be negative a sine of x plus b cosine of x. And then y double prime will be negative a cosine of x minus b sine of x. How about that? Let's plug it in, okay? Plug it into this. We have to, just suck it up and write it. So negative a cosine of x minus b sine of x, and then just add it. So I'm going to write it underneath here. Oh, why don't I be clever and write it this way? plus b cosine of x minus a sine of x, line up the like terms. You know what I'm saying? And then negative 2 times this first term, so I'm going to distribute negative 2, so negative 2a cosine of x minus 2b sine of x should be sine of x. Are we good? Well, having said that, they are like terms now, so let's add. So what I have is negative 3a plus b times cosine of x, and I have negative a minus 3b of sine of x is equal to sine of x. So that tells you negative 3a plus b is equal to 0, and negative a minus 3b is equal to 1. And we still have systems of equation 2 by 2. You know what I'm saying? Okay. Let's just, too much algebra, so let's just do it in our head. A is negative 1/10 and b is negative 3/10. Okay. Hopefully you can pull that up on your own, right? So my solution should be, oh, let's copy this. So my entire solution is this one. How did I do? What did I do? This is a weird button. It's pressed. Okay, I'm back. Therefore, my solution should be this. Erase that thingy. And minus 1/10a cosine of x and b sine of x. How's that? And that combination altogether, if you plug it into the differential equation itself, this thingy, then it will give you just nothing but sine x. You kind of get the procedure of how to do this indeterminate coefficient method.